Hi, this is Kent Brown, Senior Product Manager at Microsoft. In this walkthrough, I'll demonstrate the Windows Azure Service Bus queue, which is a way for you to add resilience, load leveling, and load balancing to your application. So, let's get started. The Windows Azure Service Bus queue provides ways to enhance your applications by enabling decoupled and offline scenarios, by collecting and holding messages for disconnected recipients, load leveling scenarios by providing a buffer between application components during peak load periods, and load balancing by enabling you to connect multiple listener applications to a single queue to spread processing over multiple machines. The queue makes it easier for developers and IT to manage each of the above scenarios for less effort and significantly less cost for physical hardware. So let's do a demo. In this demo, I'm going to show you a simple application consisting of a message sender that sends messages to a service bus queue, the service bus queue itself, and two message listeners to receive messages from the queue. I'll switch to Visual Studio and we'll get started. I've set up a simple project that you can download from Codeplex if you want to follow along. The solution file contains a common library, a sender application, and a listener application that can be instantiated multiple times. Right-clicking on the sender project, I'll select Debug, Start New Instance. The sender is a simple WPF application with sliders to set the message size and the number of messages to send. There are two counters, one showing the number of messages sent and another showing the number of messages in the queue. Clicking the Start button creates the selected number of messages and sends them to the queue. Let's set the message size to 50 and the message count to 20. I click on Start and the sender sends messages to the queue. You'll notice I don't have a listener open, which I did on purpose. I want to demonstrate how the queue is helping me to support a decoupled scenario, one where the receiving client is offline. When the listener connects, the queue will have the messages waiting so it can receive them. So let's fire up a listener. Back in Visual Studio, I'll start an instance of a listener in debug mode. The listener is also a simple WPF application with a slider to set the number of messages to receive from the queue and a Start button. The counter shows the number of messages received. I'll set the listener slider to receive all 20 messages we sent from the sender and click Start. Now you see the listener receiving messages from the queue. The listener count is increasing and the queue count is dropping each time a message is received. For this demo, the listener is simply disposing of the messages. But in a real application, we expect the listener would process or forward the message to another system or present data to the end user. Using the queue this way shows you how it can make your application more resilient by enabling scenarios where some components may be offline. Now, let me show you how the queue can help you with load leveling. Imagine application usage is approaching a period of peak load where messages are coming in faster than the listener can process them. To demonstrate this, I'll send 50 messages to the queue. While that's going on, I'll open a second listener. Now, I'll have the first listener receive 20 of those messages. I'll set the slider on the second listener to receive 30 messages and click Start. Here, you'll see the queue counts increasing as the sender is sending messages at a faster rate than the listener can consume them. This demonstrates how the queue enables your application to have a reliable level of elasticity and level the load of your application components. With two listeners running, we're receiving messages at a faster rate than the sender is sending them, and the queue count is now dropping. You can add listeners to increase capacity during peak times to get the work finished faster. More powerful listeners will receive and process more messages and reduce overall processing time. I'll stop the application and walk through the code. The queue is a capability of the service bus and is provisioned in code, so you just need to create a service bus namespace in the Windows Azure portal to use it. Once the namespace is created, you collect endpoint information from the portal. You will use these bits in the code. Next, I reference the Microsoft Service Bus assembly, which allows me to interact with the service bus. It ships with the Windows Azure SDK and can be found in the Windows Azure SDK folder beneath Program Files on your system. Now that the project knows how to connect and consume Service Bus resources, let's walk through the code that does the actual message processing. The sender and the listener projects are WPF applications written in XAML. The code that is doing the real work is in the Common Lib project. I'll talk through some of the more interesting lines. The sender code sets connectivity mode to HTTP, then it uses the Service Bus configuration data I've copied from the portal to create a Service Bus namespace manager. The namespace manager object allows me to perform management operations on the Service Bus, like get information on existing queues or create new queues. Using the namespace manager, I use a try-catch block to create a queue. If the queue already exists, my catch statement deletes it and creates a new one. You would do this differently in production, but for the purposes of this demo, I'm assured there is a queue waiting to receive messages. The queue and the sender are ready to go. I create a messaging factory, which is sort of the master object for talking to the messaging system. This involves passing in my Service Bus namespace and credential information. Then, using the messaging factory, I create a queue client, which is my connection to a specific queue. I'm sending a number of messages within a for loop. Within the loop, I create a brokered message, adding a property named data, which holds the text of my message. Because I'm sending a number of messages and notifying the UI to display message counts, I use the asynchronous begin send command to send the messages to the queue. The callback anonymous method advises the debug window and raises an event for the UI when the message is sent. Now let's look at the listener. Like the sender, the listener code sets connectivity to HTTP and uses the Service Bus configuration data to create a namespace manager. Again, like the sender, the listener uses a messaging factory and a queue client to interact with the queue. I use the asynchronous begin receive method to receive messages. When a message is received, I notify the UI to update the message count and pass the message to a process message function, which for this demo just disposes of it. And with that, the walkthrough is complete. In this presentation, we demonstrated how the Windows Azure Queue enabled resiliency, load leveling, and load balancing scenarios. We walked through the code to interact with the queue, and we showed how to configure the Service Bus and the application to use the queue. I hope you see how easy this is and the benefits queuing can provide to your applications. I recommend that you test this out yourself and find out how simple the Service Bus is to set up and use. The demo code, scripts, and snippets are all available at codeplex.com. Please also go to windowsazure.com where you can find the latest information and additional resources, including details of our current offers, information about a free trial, and how to download the SDK. Many thanks for your time.